You. All right, welcome everyone. Thank you for coming to the Engine and Generator Instrumentation and Control segment of the Raleigh Schools for EXA. My name is Jim Siffring. I'm Director of Sales at Gertz Industries. We're a packager out of Monticello, Indiana. By packager, we typically take a genset and we install it into an enclosure, put a fuel tank, that sort of thing. So that's the type of packaging we do. A little about me. I was a United States Air Force female master technician. Got my associate's degree in electronic systems technology as well from the Community College of the Air Force. Came out of the Air Force and went to work as an instrumentation and electronics technician for a compressed natural gas packager and operator. And then I went to work for an application engineer for another gas compression company. Went to work for a local Caterpillar dealer as a technician and ended up as a project manager, then a product support rep, and finally a prime power sales guy for a cat dealer. From there, I went to work for Atlas Copco as a U.S. product manager for generators and light towers, and I'm currently have been at Gertz Industries for about 7 years as a director of sales. I took this course back in 2004, so I think this has been instrumental in my career progress, and I think I applaud you guys for taking this class. So I'm a firm believer in it. So what are we going to talk about today? So module overview is and I first off, I'll just say I'm not going to read all the slides here. So I'm going to read the first few slides, and then we'll go into what it is that we're working on here later. But these first few slides I will just read to get through them. So engine, generator, instrumentation, and control. So this module covers the instrumentation for the monitoring and protection of the engine and the generator. Discrete instrumentation devices are introduced and their application troubleshooting is analyzed. Control systems are discussed for various engines and generator applications. And emission control systems, monitoring technologies are reviewed. Other various control systems capabilities are discussed, and a little bit about communications. So the agenda, what is the need for instrumentation controls? We're going to look at the tools for instrumentation and metrology, the digital versus analog signals, mechanical instrumentations, also electronic and electrical instrumentation systems, different levels of control, dedicated purpose controllers, ECMs, and a little about communications, TCP, that sort of thing, and some troubleshooting along the way. So I always start my presentations with a safety share. So this is my family, my sons, my daughter-in-laws, all the grandkids, my wife, everybody. I care about them deeply. We are in an industry that has its share of hazards. This industry obviously has places that you can injure yourself at. So take care of yourself. People are counting on you. People at home, people that you work with, other people like that. They're counting on you to be there. Would come home from work tonight, go to work in the morning as well. So if you're not qualified to do any of the stuff we discuss in this module, please stop, ask for help, get some help from somebody, whatever you need to do. But please don't do anything safe that's not safe for yourself, for the equipment, anything like that. So just keep that in mind. So, excuse me. Why do we need instrumentation controls? So what are we going to do? We're going to monitor the critical parameters of this genset. We're going to hopefully send an alarm or a warning before we hit an alarm, when an alarm is imminent. There's two basic stages to controls. You want to have a warning that says, hey, something's about to happen, and an alarm that says something did happen. So we'd like to have that warning first and tell us before the alarm is happening. But we do want it to alarm if a parameter is met or exceeded. So what we really want to do, though, is avoid a forced shutdown if at all possible. But we do want to shut it down if we want to protect the investment, to minimize damage, to increase safety, whatever it happens to be. There are a few exceptions to that. Typically with like fire pumps, there are very few shutdowns. If a fire pump is running, typically you want it to run and give its life for the cause. So but safety is really the final thing that we're trying to get to. So once we had any kind of or what we want to do with all this instrumentation controls is provide information to us. What happens, what is happening, what happens in the past, what's going to happen in the future, as much as we can predict it. We want to have some sort of point of central control, so we don't have to go over here to look at one thing and go somewhere else to look at something else. We want to have all those things available to us at a central point. We want it local, possibly sent off to a dispatch center, possibly to a building management system, something like that. So finally, and most importantly, we want to keep that genset running. So what are the parameters we look at? If we just take the engine itself, so what are the parameters on an engine? This is certainly not inclusive of everything, but many of the things we want to keep our eye on. So engine temperature, of the coolant, of the lube oil, of the exhaust system. We want to look at pressures, probably lube oil pressure, probably fuel pressure, coolant pressure possibly, turbo boost pressure, exhaust differential pressures, things such as that. Levels, what are levels? So how full is the tank? How much does this thing have in it? We want to look at coolant levels. We want to look at lube oil levels, fuel and DEF. If you've had to work with any of the new DEF systems, they won't run without DEF. Speed, as in RPM. RPM determines the frequency output of the genset, so we want to keep very close track of that. Vibration, knock, other type of things that mechanical type issues. We want to have sensing, say if there's water in a fuel system or something like that, we can sense that. Probably first and foremost these days is emissions. We want to keep track of our emissions. We want to keep track of NOx, O2, CO, all those sort of things. And then we go on to the larger scale, to the genset itself, or what's coming out the back end of the generator, the electrical stuff. So volts and current in amps. We want to look at frequency in hertz. We want to look at kW, kVA, kVAR. We want to look at power factor, excitation voltages and currents, things such as that. Is all things that we want to keep an eye on. So common system parameters that we want to, like other things that go along with the genset that may not be part of the genset. First thing, breaker position. That's a key one in my experience in the service side of the world is how often people used to get called out and the customer would say, you know, the lights are out in my building, but the generator's running. Well, how, did that breaker get tripped? Did the breaker get left in the opposition last time it got maintenance done on the genset? If we can keep track of what that breaker position is, it may save us countless headaches. Fire detection, obviously that's a very important thing. Fuel leaks, another very important thing. Combustible gas, is there a leak in the natural gas system or something? What are the door positions, things like that? What's the position of the emergency stop switch? How about fuel levels, DEF levels, radiator airflow? Is the fan belt broken? Things like that. Many, many more things that we want to look at. So what kind of tools, if we're going to be a technician or keeping track of these things, whether you're an operator, a tech, or even me as I've been a sales guy for years now, but I still carry one of these meters in my truck with me pretty much everywhere I go. A digital voltmeter, DVM, is probably the most important tool you can have as far as from an instrumentation aspect. I find these things are as valuable as a set of wrenches or a socket set or anything like that, pair of pliers. Just key to have one of these in your toolkit and a basic understanding of how to operate it. So what do we look at with a digital voltmeter or digital multimeter? We look at AC and DC voltage, resistance in ohms, current reads out in amps typically, frequency as in hertz. And what I find is this amp clamp in the main picture there, you see the one with the red meter with the yellow loop on it, is kind of a clamp on ammeter with a multimeter built into it. That's the one I keep in my truck, as a matter of fact. So you can go down to Home Depot or or Granger and buy those for less than $100 with a set of leads and a case. Very powerful tool, pretty simple, very durable. They'll live in the trunk of your car and you're behind the seat of your truck for years. Excuse me. Temperature indicators. Another great thing to have is some way to measure temperature. Basically, I have two types here. One is the non-contact on the left. And then you have a contact type that's on the right, which uses a thermocouple. We'll discuss thermocouples as we move through here. But pro tip, if you're doing a commissioning on a job site and someone comes by and wants to talk to you for a while, excuse me, my apologies. That infrared thermometer is a great tool. You can give that to somebody and they'll go spend the next half hour looking at temperatures and things like that. So anyway, okay, next tool you might want to consider having if you're ever going to be commissioning UPSs, transfer switches, anything such as that, is a phase rotation tester. So what is that? It's just a device to tell you what your rotation is. Is it ABC or ACB? And that's a very important thing to look at, especially if you're commissioning transfer switches, things such as that, where you're going to be switching from, say, a utility source to a generator source, or maybe from a generator to a generator. You want to make sure that your rotation is in the same direction. Excuse me. Otherwise, things such as three-phase motors and things like that will end up having to spin backwards if your rotation is backwards. So can cause a lot of damage if you don't have that correct. Again, those things are really inexpensive. I think you can pick those things up at Granger again for less than $100. The one that you see in the main picture there is also mine. It's I think I bought it years ago. It still works just fine. Back then, I probably paid less than $50 for it. Instrumentation tools, also a Megger insulation tester, Megger, a high pot, sometimes they're called, things like that. What this device does is applies a voltage to conductors, and you're looking for any kind of current flow between conductors. And so if there's any kind of insulation leakage, these things will find it. So there is a little bit of skill to operating one of these things. You have to have some training, some knowledge of what you're doing there. But this is one of those service tools that you really need to have if you're doing like quarterly or annual maintenance on a generator set, especially in a standby application. Much more common in like high humidity areas, things like that, where what happens is the insulation in a generator end will collect moisture and we'll start to have insulation leakage. And it may be very, very little bit, but over time that insulation starts breaking down and then you'll end up with an arc internally in that generator end. So if you can discover that, and really what it comes down to is you're going to chart these values. You'll find out what your insulation leakage is and then chart it over time. And that'll give you an idea if you need to have the generator in cleaned up, baked, or heated up to get the moisture out of it, anything like that. So if there's any questions or any comments along the way, please raise your hand. Nathan will interrupt me and stop me, and we'll discuss it at further length. Moving on, manufacturer specific tools. So typically, for manufacturer specific tools, you'll have a communication adapter. You'll typically need a laptop or some type of a device to communicate with it. And typically you'll need the software and you'll need a subscription. The CAT is on the right, the Cummins product is on the left. Pretty much all the major manufacturers have some type of a communication tool or specific electronic tool to work on the new electronic engines. Other stuff that's nice to have. Sound level meter, again, another one of those tools. Sound is kind of a dark art. It's in my opinion, it's a bit of a black magic to understand sound and all the octave bands and all the rest of that stuff. And but if you've got one and can take a quick measurement, sometimes it'll it'll be to your benefit. So other devices such as a combustible gas sensor, oscilloscope, if you've got the ability to use it and know what you're looking at, can be really nice tools. Scopes are typically more expensive. That one there, that Fluke scope is, probably a couple $1,000s at this point. Other little things such as alligator clips to go on your leads of your multimeter can be really handy. So nice stuff to have if you're going to carry these things around with you. Other things we want to look at, say torque wrenches, scales, weight scales type of things, flow meters. Often if you're doing some projects, used to have to do some projects for some customers where they wanted to know total fuel consumption over a certain amount of time. And really the best way to do that is to weigh your fuel before you start and weigh your fuel when you're done. And that'll tell you how much fuel you've used over that particular amount of time and that much load. You can also do that with flow meters, but of course you've got to measure both the fuel that goes into the engine as well as what comes back out of it again. But all tools that you might need to do, typically in a commissioning test or maybe some doing R&D testing if you happen to be involved in that sort of thing. Other stuff that might be testing per specification. You'll see this in specifications where you have to have, give measurements in certain things. You'll be able to document what type of measurements, things that you're looking at. So measuring tape. I point out this particular measuring tape that you see on the screen. It's got inches and centimeters, and that can be pretty handy. There's a lot of drawings you see that will have maybe the drawing from the architect is laid out in inches and feet and SAE, and then you might get the engine drawings from a manufacturer, and they might be in millimeters or centimeters or something like that. So some of those are kind of handy if you can find that tape that has both inches and centimeters on it. Can be pretty handy for this sort of thing. A caliper, lower left screen, is a very valuable tool. Can tell you all kinds of stuff. Feeler gauges, other things such as that. So good things to have. Let's talk about calibration or metrology. So metrology is the science of weights and measurements. And really what it is metrology is saying, or what the science is being able to trace your measurement back to some central standard somewhere. In the world, the BIPM, which I won't try to pronounce, the Bureau International des Poids de Mesures, or whatever, someone who can speak French can say that much better than I can. But they are the global holder of the final standards of all measurements, the seven different segments of metrology, and those then the NPL, the NIST here in the United States. NIST is National Institute of Standards Technologies. They'll get their standards from the French lab there. The Japanese, the Brits, everybody else in the world goes back to the French to find their final, to say that an inch is an inch, or a meter is a meter, and a volt is a volt, and a kilogram is a kilogram. From there, those standards are held to all the labs that come underneath it. So any lab that has NIST traceability can trace their standards back to the French lab, the BIPM. So I mentioned the 7 different aspects of metrology. So meters, kilograms, seconds is time, amperes, current flow, candela, which is light, Kelvin, which is temperature, mole, which is molecular weight. So those are the 7 standards that we measure everything, that everything basically comes from. This is just we want to talk about having your standards calibrated. Whatever your test equipment is needs to be calibrated, needs to be up to date. You'll see this little segment here, item D, where test instruments shall have been calibrated within the past 12 months, traceable to NIST calibration services and adequate for making positive observation of test results. and then make calibration records. But anyway, that's a very standard line in a specification for a genset. So what does that mean? It means that if you go out with your multimeter and test the voltmeter on that genset, and you say, yes, that voltmeter is reading correctly, you have to have your meter calibrated by somebody, and that calibration laboratory has to be able to be traceable back to NIST, which in turn goes back to the French BIPM lab. That way we know that everything is calibrated against a known standard, and we're not going to have any of that any of the issues that may arise with having equipment that doesn't read out correctly. So what does metrology or calibration provide? Now, metrology and calibration are not necessarily the same thing. Calibration is just basically checking your device, your tool, to make sure that it is accurate, that is within a standard, that, you know, typically a device has a plus or minus tolerance that it must fall between. Calibration is doing nothing more than testing your tool that it falls within the tolerance of that to a greater known standard. Metrology, again, is a science of weights and measures, and provides us a way to do that. So metrology provides calibration of equipment to a known standard. If you need to adjust that tool, we can adjust it, and it provides traceability to those standards. There's a rule in metrology, the 4-to-1 rule, that basically means if you're gonna test a voltmeter that's on a genset, and that voltmeter that's on the front panel of your genset is good to say plus or minus 2% accuracy, the device you have to test it with has to be 4 times greater than that, or plus or minus 1/2 of 1%. So that's what that 4-to-1 rule is. If you have a 4% meter, you need to calibrate with a plus or minus 1% meter. So, what are some of the electronic things we do? Voltage, current, frequency, resistance, mechanical things that we need to keep testing and calibrated is pressure, temperature, distance, weight, sound, torque, that sort of thing. Pretty much all those tools that measure any of those parameters that we're talking about need to have some sort of certification. I know at the plant that I work at, we even have tape measures that are calibrated. It's funny, you see it's a Stanley 25-foot the tape measure, and it's got a calibration sticker on it, which always seems funny, but when you look at it, that's something you need to do, because tapes do wear out, the ends get loose, things like that happen. They need to be calibrated. Okay, so now we've gotten all this. What are we going to do with all this instrumentation? So NFPA 110 is kind of the guiding NFPA standard that is pretty much the basic standard for all building type stationary standby emergency generator sets. NFPA 99, of course, goes to medical facilities and refers back to NFPA 110 as well. But pretty much NFPA 110 is kind of the basic standard we have to work with. So what do we need to satisfy the requirements of NFPA 110 for instrumentation on a genset? Well, the first thing we have to have is a panel mounted switch. It's got to have 3 positions. It's got to have an automatic switch, or automatic position, an off position, and a run position. That's a minimum. It's got to have shutdowns or lockouts for all of the following 4 items, and that's overcrank. Overcrank is failure to start, overspeed, low oil pressure, and high coolant temperature. You need to have some sort of a remote emergency stop button. You need to have an AC voltmeter for each phase. You can switch between them if you want. That's fine. Same with the AC ammeter for each phase. You got to have a frequency meter, and you have to have some kind of a voltage adjusting rheostat to provide a plus or minus 5% adjustment from nominal. So what's that look like? This being, this is just an old cat panel. I think this is what they used to call the Redcos, but it does everything we're talking about here. If you go on the left, you got an engine oil pressure, you've got a coolant temperature. You'll see that on the very lower line, there's a low lube oil pressure, excessive water temp. You've got an overspeed and an overcrank. Those are all trip devices, and if they trip, they light up. You got a reset button between them. Over in the lower left, we have a battery voltage meter. We don't have to have that. It's a nice feature, but we certainly don't have to have it according to NFPA. You've got the amp meters and the hertz, or frequency meter, and the AC voltage meters up on the top. The switching in the middle there that'll switch between those different devices. Then you also have you actually have a 4-position switch here, which will give you the manual, off, and auto position, as well as the stop position on this particular one. And then on the far right, you have the voltage level rheostat, which will give you your plus or minus 5%. So this meets the minimum requirements, plus it has a few little features that you don't necessarily have to have. But even as old tech and old school as this thing looks, it meets all those parameters. So let's talk about signals. What are the signals that we're going to get back from whatever it is we're looking back at to the device that we're using to monitor it? So we have a discrete or a digital signal. What is a digital signal? A digital signal is one of two states. It's a yes or a no. It's a high or a low. It's a 1 or a 0. It's an on or an off. That's the only two states it can be in. So what is that? A switch, a relay, a solenoid, a valve that only closes or opens as only two positions, a pressure switch, or examples of that: pressure switch, a temperature switch, thermal switches, overspeed switch, or maybe a water and fuel switch, something like that. Basically, it's on or off. And as a note, so is this device the digital device, or is this the device that's digital? And since I can't see any hands raising, I'll just say the switch itself is the digital device. It's on or off. It's one of those two positions. The lower one is a digital display of an analog signal, of an analog thing. So that temperature could go anywhere from minus whatever to positive and well over 200. Who knows what it happens to read, but that's an analog signal, but it's a digital readout of it. So the digital device itself is actually that switch. So as we bring up analog now, so what is analog? Analog is a signal that varies over a range. It's proportional to some quantity of some kind. So if you look in the lower right, the thermocouple versus temperature chart. So as temperature goes up, then the voltage out of that device goes up. So it's proportional. Generally speaking, it's a fairly smooth line, but you can chart all those things. It can be positive. It could be negative. It could actually come from the upper left and go to the lower right. So what are variable signals? Resistance, voltage, DC current or AC current, frequency, capacitance, all kinds of different signals. One final one I want to make sure you're aware of is PWM, pulse width modulation, PWM. So PWM, if you look at that upper one, the upper line, you'll see it's on for 10% of the time and off for 90% of the time. So you'll notice that the upstroke of that square wave is the same on all three charts here, all three graphics. And so the frequency is the same of that signal. That signal is a constant frequency, but the amount of on time changes variable and that can be anywhere from 0 to 100%. So in these three examples, you'll notice the top one is a 10% on signal, the middle one is 50% on, and the 90% on is the bottom one. So what does that mean? It means that on and off signal can be proportional to some value of something else, whatever it is that we're looking at. And we use PWM for all kinds of different parameters. So is PWM an analog or a digital signal? Well, PWM is actually a method of digitally encoding an analog signal. Okay, on to the next here. Okay, so let's look at a mechanical versus electrical type device. So on the left, you'll see a mechanical or a direct reading type device. This is a pressure gauge, board on tube pressure gauge. What do we get in mechanical reading? So pressures, levels, temperatures. If you've got a, some device that that looks directly or it is looking at a parameter and you get a direct readout on it. Visual, you can see right exactly what's happening. On the other side, you'll see a sender, and that's an electrical signal. So examples of that are senders, transmitters, transponders, RTDs, switches. We'll talk about a lot of these things as we move through this module here. But electrical devices that you can't tell what's going on in there, it sends a signal back to something that's actually monitoring that device. So let's talk about measuring pressures. All the different methods we can use to measure pressure. So diaphragms, board on tubes, bellows, sound senders, transmitters, things such as that. Lower left, you'll see a board on tube gauge. Over on the upper right, you'll see a piece of tubing. What in the world do we use a piece of tubing for measuring pressure? Notice in that piece of tubing, there's some water at the very tip. I wish I could show you this, but my cursor's not working. But anyway, so if you look at specifications such as inches of water drop, pressure drop over, say, a radiator, across a radiator with a fan, and maybe you get 10 inches of water drop, pressure differential. Well, how do you measure that? So we'll fill this piece of tubing, maybe 20 feet of tubing up, full of water, or close to full, not full. Want to leave some room at the top of each side of that. And if you hold the two ends together, the water level is going to equalize between the two. Now, if we take one of those ends and stick it into a different area where the pressure is different, say one on the inlet side of a radiator and one on the discharge side of a radiator, and we measure the difference in water column between one end of the tube and the other, we can tell how much water pressure, or how much pressure drop across there by looking at the inches of water column. So when you see a radiator might have, say, 5 inches of water column or 5 inches of water, that's exactly what they're looking at. And so then there's, of course, other gauges that'll tell us all that sort of thing. But in the most primitive of ways, that's how you can measure that. So let's talk about board on tube gauges. Board on tube is probably the most common pressure gauge you're going to find out in the world. And really all it is a brass or stainless steel or other type of material with a piece of tubing on the top. You'll see this piece of tubing up here on that upper left corner picture. And once you apply pressure to that fitting on the bottom of the device, that that curved piece of tubing will want to straighten itself out. It's just the physics of it. It'll want to straighten that tubing out. And we can take that piece of tubing and that end and tie it onto a mechanical pointer, and it'll give us a visual representation of what's happening in that tube. As you increase pressure, the thing straightens out, moves the pointer, and we can calibrate that to read out in whatever type of pressure you want it to say. You can also take that device in the lower right corner. You'll see the photo of the device with some wiring coming out of it, and that tubing end is connected to some type of a device that gives you an electronic signal out. When as that tube moves, it'll give you a corresponding movement across those two black devices, and it'll give you some sort of an electronic signal out. So look at bellows pressure. So I keep this graphic in here because to me it's counterintuitive. So you'll see the two devices within the graphic there. And basically it's a bellows. You screw that into some area that you want to measure the pressure on. For me, it seems that if you would increase pressure, the device would get shorter, like on the left. That's actually the natural state. If you apply pressure to it, it actually gets longer. And to me, that's counterintuitive. That's the reason I put the graphic in there, just to be aware that what's happening on this device may not be what you think it's happening. So the bellows expands as you add pressure, and um, so anyway, that's what I want you to keep. But those type of devices, I don't see a lot of them, but they can be pretty accurate. So also we get to things like service indicators. These are not really measurement devices. Um, like I said, they're indication only. They're sensitive enough to tell you that in this application, these devices are used for measuring air restriction across an air filter. So if the air filter starts to get clogged, it creates too much vacuum on the inlet to the engine, and it'll start indicating on that device. Once that the red gets pulled down into wherever it's someplace or you want to do the maintenance on that air filter, you can reset it. Typically on this type of device, you push the top and it clicks and the thing resets itself, and you're off and running for the next series of hours where you're watching that air filter. So it's not terribly accurate, but you don't really need accuracy. It's mainly giving you an indication of when that air filter needs to be serviced. Repeatability is probably more important, so you don't end up clogging up a filter too far. This graphic I always find important because what you're looking at is this. So what we're looking at is temperature. You'll notice the Murphy switch gauge there says temperature on it. But then you look back at the graphic and it says, well, we're applying pressure to that temperature gauge. That doesn't seem to line up. So what we're doing is, as that coolant in the graphic shows is heated up, it heats up, and whatever the liquid is in that device, in that piece of tubing, heats up. It creates a vapor and creates a pressure, and that pressure is applied to the back of that gauge, that board on tube gauge, and it gives us gives us an indication. And really the point I'm trying to illustrate here is that what you're looking at may not be what you think you're looking at. You're actually looking at a pressure, but it's indicating temperature. So just keep that in mind as you go through your time and looking at these devices, that maybe a pressure gauge is actually is actually a temperature gauge. Um, keep in mind you may not have a device actually looking at temperature, maybe looking at something else. Okay, we'll talk about pressure senders as well now. This is a very common device. You'll see the steel can. It's just a resistance type sender. Typically, they'll have 240 ohms for a low reading and 33 ohms for a high reading. Not adjustable. You'll buy that device. So if you need, say you're looking at it to look at engine oil pressure or something like that, maybe that device will read 0 to 100 psi or something like that, and you can calibrate that to a gauge, and that gauge will say, okay, at 240 ohms, I'm going to read maximum at 33 ohms, or minimum. Sorry, 240 ohms, I'm going to read minimum. At 33 ohms, I'm going to read maximum, and set up your gradients between there. And you got everything you need there. So typically you only have one position. You'll see the screw connector on the left hand side of that device. Ground is actually the case, so you'll actually ground the other end of the circuit to just chassis ground, whatever it's screwed into. Typically there's no adjustment to a device like this. They're super common. You'll see these things on all kinds of engines. It's pretty easy to troubleshoot. Put your ohm meter across it from the metal case to the pin itself that's on there. It should give you some resistance of some kind. And like if there's no pressure applied, it should read somewhere in the range of 240 ohms. Be careful to disconnect whatever wire is on there, because that may skew your reading. If you apply full pressure, it should read 33. That isn't a set rule. That those resistances may change from device to device, but for this particular one, it's pretty common. So you can use that. Most often, if something's gone bad, you put your ohm meter on there and you just see an open or a short, and that it's bad. So pressure transmitters, typically something like this will give you a 4 to 20 milliamp signal. We'll talk a little bit more about 4 to 20 milliamp signals as we go through here, but generally speaking, if we look at that lower graphic there, you see a 12-volt DC supply, you'll see your meter, and you'll see a transducer. We're running a current. They provided a voltage, which will give us a current that'll flow through that transducer, and that transducer will give us a proportional current reading out for whatever measurement it's taking there. So say at low pressure, maybe at 0 psi, it's gonna flow 4 milliamps through it. And if you say, let's just say the high end is 100 psi, at 100 psi, it would flow 20 milliamps. And with the remaining 16 milliamps between the 4 to 20, you can scale that to, so say at 50 milliamps, you'd be looking at whatever the number would be, 12 milliamps. Or 50 psi, you'd see 12 milliamps of current flow. Those ranges are typically printed on the label itself. You see on the right hand side, you can see that the range is printed on there. You can use them for oil pressure, coolant pressure, manifold pressure. You can also get these things that have the ability to talk on a CAN bus, the J1939. We'll talk a little bit more about J1939 as we get through this module, but that's effectively the protocol that pretty much all modern engines talk over. Troubleshooting, you can put your ammeter in series with it and compare it to whatever chart is or whatever it is you're looking at. It typically will have a chart you can go online and just look it up for that particular part number. All right, let's move on to level measuring methods. So how are we going to measure levels, like say amount of fuel in a fuel tank, or the amount of coolant in a radiator, or things such as that? So we have float systems, we have liquid contact, we have optical, capacitive, ultrasonic radar, pressure devices, things like that. So probably one of the more common ones you'll see in the right-hand graphic is just a variable resistor that's on a float arm. So that arm is connected to a variable potentiometer or volt or a resistor, and as fluid goes up in the tank, the arm is taken across that variable resistor and changes resistance out. So again, we're using that 240 to 33 ohms scale. That's common. It's not a rule, but it's very common. Use these a lot on diesel fuel tanks. You won't see these in gasoline tanks at all, but you will see them in diesel tanks. And again, troubleshooting with this type of device is very simple. The resistance across that device should change with the sweep of that arm. More common, it'll read something completely out in the weeds, like really high resistance, or it might read 0 resistance for a short, might be completely open. Float type switches, real common in a float switch are reed switches. I'll show you an example after we look at this, but a reed switch is basically a switch inside of a glass vial, and this little thing is, less than a 1/4 inch around. They're small, skinny glass vials, and in the presence of a magnet, they'll close or open, change state, whatever that happens to be, just like the graphic shows. So as you move the magnet closer to the switch itself, it may close, it may open. It's however that particular device is set up. But where they're used and things like that is in devices such as this, like a multi-float stack switch or single switch stack. And you'll see the floating the floats that are on that shaft, and they're limited to how far they can float, but they can set those in all kinds of different areas. You can order these as you see here. They would be ordered like that, or you can custom make them yourself. But there's a bunch of float switches. Inside those little floats is a magnet, and then inside the stainless steel rod that goes down through all of them are a bunch of those little reed switches. And so as the floats up, that magnet will come in contact with the reed switch itself, change the state, and give you some kind of an output. More float type switches, Murphy switch gauge, very common in the industry. So basically there's a float inside this device. And as the fluid level goes up, you'll see over on the left-hand side, there's a pipe fitting. You'll tie that into, say, a radiator connection, or into a radiator or something. Set it to where this device will be set at the level that you want that tank to be set at. And then there's a float inside there. When fluid comes in there, it floats the switch, and you'll see metallic contacts in there and give us a signal out. The right-hand one is very similar type device, does pretty much the exact same thing. Level switches. Liquid contact type device. So on the upper right-hand corner, you'll see a contact switch. So it's just sitting there saying, if I see coolant, I'm okay. If I don't see coolant, I change state. That's a super common device. I think that's off a John Deere engine I took this shot on. And basically it's a device that, like I said, when it sees fluid, it changes state. If for some reason that goes below that, then it'll give you some indication out. Typically it'll open. Okay, let's look at temperature measuring methods. So we have all kinds of different types of temperature measuring methods. We have the chemical and liquid filled systems like the glass thermometer, like that graphic I showed you earlier that said that there was a liquid that expands to create a pressure. Then we get into thermocouples, RTDs, thermistors, all types of device like that. So we'll talk about each one of these. Thermocouples. So a thermocouple is made by welding two dissimilar metals. So that junction will create a voltage across those two dissimilar metals. Those two dissimilar metals are, say, in this in the photos on the right, two pieces of wire, and we join those two pieces of wire. You literally have to melt the two pieces of wire together. Then there's a voltage created across those two, and that voltage will change with temperature. So as temperature changes, voltage changes commensurately, and you can chart that. And actually, it's a fairly accurate way of doing things like that. So very common in the industry is a J-type thermocouple or a K-type thermocouple. Both of them, J-type is super common. With thermocouples, a J-type is an iron constantan. And so you have one wire that's made of iron. You have one wire that's made of constantan. And you join those two together. So those two wires would get welded together. But you'll see the colors on there. The one wire is white, one wire is red or has red insulation, one wire has white insulation. Those are how you tell what your thermocouple types are. If it's red and yellow, you got a K type. If it's red and white, you've got a J type. And there's a whole bunch of other types of thermocouples. These are by far the most common in the industry, but you'll see it. And and really all you have to do is Google, the different types of thermocouple color codes, and it'll tell you what they are. Now, one thing to note, like on the J type, the red is the negative side, the white is the positive side. Similarly, the K type, red is negative, yellow is positive. That's different than most other DC wiring because red is typically a positive lead. White is often common. So keep track of that. That they are really, that's an indication of what the type of device is, not necessarily what polarity and things like that are. Really good for high pressure, high temperature, high vibration type applications. Really easy to troubleshoot with the DVM. You can't really read the voltage on it because they're actually millivolts. So you have to have some kind of a device that's designed to read a J-type thermocouple or a K-type thermocouple or whatever thermocouple you have. But if you isolate it and put a DVM on it, digital voltmeter, and put it on ohms, is really easier. You just measure it, and if it's got resistance, or it looks mostly like a short, really, it looks almost like there's very little resistance on that wire, it's probably good. If it shows open, then it's no good. So we've got a thermocouple. This particular chart down here will show what would be the voltage output on this particular thermocouple at 32 degrees. Well, we'd go over on the left-hand side, we'd see 30, and we'd go across to the 2 for 32, and we'd have 1.285 millivolts. A thermal well. So what is a thermal well? Thermal well is really a device that protects the sensitive type electronic device, the thermocouple, sensor, RTD, whatever it happens to be, in that process, gas or fluid. So we screw that thermal well down into the pipe that is carrying that process gas, whether it's exhaust, whether it's coolant, whatever it happens to be, and then we put that sensor down into there. So the sensor isn't exposed to the maybe the temperature will come right through, but it won't maybe be in a nasty environment, exhaust stream or coolant or water or whatever it happens to be. So it's really just a device to protect the sensor. RTDs. RTDs, resistance temperature device. So as opposed to the thermocouple that gives a voltage out, which is proportional to a temperature, these things actually change resistance with the temperature. So that's the difference between thermocouples and RTDs, is one changes voltage output, one changes resistance. So they can be made out of all kinds of different type materials that give you all kinds of different resistances. So platinums, copper, nickel, platinum, and they can be in different configurations. You might see these with 2 wires, you might see them with 3 wires, you might see 4 wires. Typically, the 2 wires, if you've got a device that's very close to the instrument that's reading it, then you don't need the 3 and 4 wire configurations. The 3 and 4 wire configurations mainly are there for lead length compensation. So they can be quite accurate. You can up into pretty high temperatures. You almost always have to use some kind of conditioning electronics to give you some sort of a readable output. And you have to have isolated circuits on these, so no common grounds. Again, troubleshoot it with a multimeter on ohms. If you get some sort of resistance, it's probably okay. If you don't have any kind of resistance, or it's way high or something like that, you might have a problem. Here's a transmitter that shows that RTD type of device. So on the bottom graphic there, you'll see the 0 in the span. That's how you calibrate things. 0 is going to be your 0, obviously. Whatever your low setting is, span is going to be your high setting. So if it's a device, it's going to meet a maximum of, say, 500 degrees. You would set that up for 500. And then here's that 4 to 20 milliamp loop we were just talking about earlier. So you've got a 24-volt DC source and some kind of a milliammeter, and that device will give you the commensurate current through that circuit. On the lower bottom, you'll see the plus sense, minus sense, and negative. So this happens to be a 3-wire RTD that's going into this thing. So so you're looking at the plus minus, and then you have a negative sense lead as well. Thermistors, a thermally variable resistor, very similar to an RTD, but different in a few ways. Is in there a simpler device. Typically have a lower range, things like that, much less expensive. They're available as a positive and negative coefficient. So it may be that resistance goes up as temperature goes up. It may be that resistance goes down as temperature goes up. But they're cheap. They're pretty easy to install, all that kind of stuff, but less. Typically it's just it's a less expensive way to measure temperature. Again, troubleshooting is put it on a meter and check the ohms across it. Typically, a sender is basically one of these things, thermistor, stuck into a heavier case. They're a little bit more durable type device. So, but again, very similar device to thermistor. All right, let's talk about vibration measurement. So A couple of different things you can look at. One being just a basic switch, as in a magnetically latched mass displacement device, and I'll show you one of those here as we come through. Effectively, a device that's held together by a magnet, and if you hit it too hard, it breaks the connection with the magnet and opens up. Or you got analog type signals that'll give you some sort of signal out: accelerometers, velocimeters, displacement devices. So what do they use for? They use for knock sensors, vibration tracking, shock detection. So vibration switch, you see the red device in the upper left. That was the old standard Murphy shock switch, is what we call them. And really all it is a contact that's held together with a magnet. And you can adjust the sensitivity or the amount of pull that magnet has on that arm. And they went into things like rental sets, rental generators, rental compressors, things such as that. And if the device took a shock, say it got dropped off a crane or a truck, as it's being moved from someplace to another, and it, got into an accident or something like that, it would break that connection. Then the rental company could tell that something had happened. Then we move into like the lower graphic with the blue device. It'll give you all kinds of it'll still do that shock sensing, but it also gives us all kinds of other input, such as vibration and knock sensing and things such as that. And a lot of times all they do is open or close a contact. May not even give you any kind of live data out. All it is looking at what kind of impact that's happened, or things such as that. Or you might have them that are more comprehensive, give you a signal out, something like that. Accelerometers, they can be a strain gauge, resistive bridge, piezoelectric, all that kind of stuff. Typically, they're using a 4 to 20 milliamp or a 0 to 10 volt output. 0 to 10 volts is very similar to 4 to 20 milliamp, but the 0 is 0, and as opposed to 4. Requires conditioning electronics. So you almost always have to have some kind of a device that can actually take the signals coming off of here, convert it into something we can actually look at and use to go into our control system. But digital outputs, often that conditioning electronics will give you a PWM signal. Obviously, sometimes they're a set point in there. You can say, I can accept up to X amount of vibration or X amount of acceleration before I trip, and then that set point is variable. You can make these things to be quite accurate, but they can also be quite fragile. A piezoelectric device is basically a crystal that oscillates at a certain frequency when you apply electricity to it or apply a voltage to it, and those crystals can actually break. So they're not used a whole lot these days, but anyway, you'll see that in a lot of older equipment. Troubleshooting is definitely more complicated. You probably have to check your power supply, check your outputs, things like that. You may take some specialized devices to be able to actually troubleshoot one of these things. Frequency measuring. So how do we measure, say, RPM on a gen set? So magnetic Hall effect pickup. Oops. So there's a couple of different ways. Active ones, which is basically a powered device, or passive, which is like what you see in the upper right graphic there, which is, generally speaking, it's a piece of steel with a little bit of a magnetic charge to it, or it's magnetically well, it is magnetic, I'm sorry, and then has a coil of wire around it, actually about a zillion wraps of really fine wire around it. And if you run a piece of iron, something ferrous, across that tip, then it changes the magnetic flux in that magnet, which induces a current into the wire itself. So really common device. If you hear things like MPU, mag pickup, that's what it is. And these things will typically screw into the bell housing right above the ring gear, the starter ring gear, and it'll sit there and watch the ring gear teeth go by. So here's the graphic on how that works. So again, the ring gear is going to be turning below that device, and it'll induce a voltage into those, or into that into the device, and you'll see those signals coming out of the wire on the connections coming out. Okay, optical speed sensors, similar. They look similar a lot. Often they look similar to an MPU, but what they are is they provide a light source, and they have a device that looks at the light, that can receive the light. So a transmitter and a sender looking at light. So it's looking at the reflective light coming back into the device. And so if you put this on, say, a shaft or a fan, and then you'll have to have some sort of reflective type, typically, like a piece of white tape or something like that on a fan blade, and you can see how many times that fan blade goes by, because it catches the reflection of that as it turns. Typically, that's only what's one pulse per revolution, whereas on the ring gear, you're going to get a pulse for every tooth on that. So if you got 150 teeth on your ring gear, you get 150 pulses per revolution on the engine. Whereas this device, you only get one pulse out for every revolution. Other places to pick up speed sense or something, if you're looking to have something give you a speed feedback, ignition systems, J1939s will typically give you some sort of a speed output. Alternator, you can pick up some leads off the alternator, off the voltage regulator, and get some signals out of there. And sometimes you just want something as simple as a mechanical speed device, a mechanical speed switch with flyweights. Don't see those a whole lot anymore, but you might see them in older devices, older engines. So it's 5 minutes after. How about we take 10 minutes for a break? Come back at a quarter after the hour, and we'll finish this segment up.
We'll be back at a quarter after.
Yeah.
Everybody?
You're all set?
All right, pick up. All right, thanks, Nate. All right, picking up where we left off. So we've talked about a bunch of the stuff that's coming off the genset itself. Let's talk about some of the electrical things we're going to look at. So current transformers, CTs, you'll hear that term now and then, CTs and PTs, current transformers, potential transformers. What is a current transformer? A current transformer is a device that allows allows you to read the current flow through a device, a non-contact sensing device. So what is that? It's typically they're rated in 1 or 5 amp output and some sort of an input. So if you see for example, a device that says 200 to 5 on it, it means that at 200 amps. So if you got a conductor going in the center graphic, you see the black device that has a hole in the middle. If you put a piece of cable through there and flow 200 amps through that conductor, then you will get a 5 amp output on the connecting pins on the top of that thing. So that's a 200 to 5 CT. Now that can be anything. It can be 1,000 to 5, might be a couple thousand to 5, might be 50 to 5 or 50 to 1. The first number, that 200, is going to be what it's rated for current flow through a conductor. And then the second number is going to be typically either a 5 or a 1, which is your corresponding output current. So on the far right hand graphic, you'll see there's a current transfer on the neutral. That's a neutral CT. So what we're looking at is current flow through the neutral side of that device, of that genset. On the left hand graphic, you'll see that amp clamp around a piece of cable. It's the exact same principle there, doing the same sort of thing. It's just that we're going to read the current directly on that multimeter. Okay, PT, potential transformer. What is potential? Potential is voltage. Voltage and potential are pretty much used interchangeably here. So it's a voltage transformer, potential transformer, same thing. A transformer that reduces the voltage for instrumentation. So So say your control panel can only take up to say 150 volt input or something like that. Yet you've got a 480 volt genset, or maybe you got a 4160 volt genset. You need some type of a device to lower that voltage down to where your control panel can actually see it. So there are different ratios. Obviously, the device on the right, the yellow one, is a Caterpillar one. It's a Cat CT or a PT, excuse me. Graphically, you'll see it in the middle schematic there, where you're looking at phase A, phase B, and phase C, and neutral, and how it's wired into some transformers. Those transformers can go through some fuses, which you'll see at the top of that device, and it goes into the controller itself. Another on the left is just another universal type part. Transducers. Sometimes you can get a device that does all these things all in one and give you some outputs that are a little bit easier and to use and to go into some other device. This is a DIFE product here, but combines both the PTs and CTs into one device really, and gives you an output. You can use it for 4 to 20 milli output, or 0 to 5 volt, 1 to 5 volt, that type of thing. So in addition, it can also give you things like phase angle and power factors, things such as that. NOx sensors, NOx, oxides of nitrogen. So the device that's used to measure nitrogen oxides in an exhaust stream. It's used for EPA Tier 4 engines, pretty much every year, Tier 4 engines, as well as natural gas engines these days. Oxygen sensor, O2, or sometimes they're called lambda sensors. It's all the same thing. O2, oxygen, lambda, same device. That measures the amount of oxygen in the exhaust stream. So used in a lot of EPA Tier 4 engines, but also used in rich burn or stoichiometric spark ignited natural gas engines with air fuel ratio controllers. Often that's the input to an air fuel ratio controller that gives it the feedback loop to tell the ratio controller what it needs to do, whether it needs to add fuel or reduce fuel. One thing to note, they shouldn't be energized when the engine is not operating. Typically, these elements are heated, but if they're heated and they don't have an exhaust stream going across them, they'll typically burn out. Now, that happens pretty much automatically on pretty much all engines these days, but just keep in mind. So a NOx sensor versus a NOx sensor, KNOCK versus NOx. Okay, not the same thing. So if you're at a parts counter and someone calls and says they need a NOx sensor, make sure you're asking, is a NOx sensor, NOx is a device to measure oxides of nitrogen in an exhaust stream, and a NOx sensor is a device, it's accelerometer. Usually it's a device to see if there's mechanically anything happening, or mounted on a cylinder head typically, or on a block, and it's looking for detonation and pre-ignition, things such as that. Okay, so we've got all these input signals. Now we decided we need to shut down the engine. So what do we do to do that? So shutdowns and lockouts on a spark ignited engine, SI spark ignited engine. So well, how do we do that? How do we shut the engine down? Well, if it's got a distributor type ignition system, we can just simply remove power to the ignition. If it's a magneto or a capacitive discharge ignition, we can ground the ignition system. If it's electronic, we can just interrupt the power or give it the digital input to shut off. In some cases, maybe we want to shut the fuel off, so we close the fuel valve. That device on the right is a fuel valve. We can just tell it to close. Here's another fuel valve, very similar, just that's what they typically look like out in the field. Okay, now if we got the same issue with a diesel engine, we want to shut that diesel engine. There's no ignition to shut down, so we're going to have to turn fuel off or turn air off. So we'll close the fuel valve, close the fuel rack, or air shut off, we can close the air intake. Typically, we try not to do that unless it's an emergency, but you'll see that on offshore equipment, a lot of gas drilling equipment, things like that, where if for some reason a diesel engine, you want to shut it off, but it starts to run away, If it's in a heavy, say you've got a gas leak, and on a drilling rig, that gas can get into the engine and be uh, enough fuel to keep the engine running, which is not something you want to do. So in that case, you would shut air off going to the engine as well. Fuel valves, energized to run. Sometimes you'll see them energized to shut down as well. It's very much the standard way of shutting down an engine for especially mechanical engine. Troubleshooting wise, you've got typically a couple of connections. You can check across those pins that you'll see with the nuts on them. See if there's resistance on those coils. You can jumper to a battery and see if you can feel it click. Just be careful with them though. They might need it. They might have a current limiting resistor somewhere else, so you might just want to just check to see if it clicks, not click and hold. Fuel rack solenoids. So mechanically injected engine as well. If you've got a mechanical engine, you can put this on the back of the rack and it'll either push it in and hold it, or pull it in, hold it shut. So again, troubleshooting is a lot of times just checking the coils in the thing. A lot of times these things will have two sets of coils. One is the energize and one is the maintain. And again, once in a while, they'll have external resistor for current limiting. Diesel and electronic engines. So how do we shut off fuel to an electronic engine? Of course, we can shut fuel off. Excuse me. Modern diesel engine, typically an injector is really just kind of a valve. So if we don't energize the valve, it can't inject fuel into the engine. Again, we can shut off air going to the engine. We can do a digital contact to the ECU, which would tell the injection to stop working. We can put a digital contact to the governor, which would cause it to go to zero. Different ways such as that. Okay, so we talked about all these different devices, and here they are. This is I believe this is a Tier 4 interim engine, but this is a Volvo TAD 16-liter diesel engine. And all these different devices that we've been talking about are right here on this engine. So it's a pretty common engine these days, and you'll see all these different connectors, all these different pieces that are being used on this engine. Schematically, this is the exact same thing. This is the schematic for that engine I just showed you, but they're all right here. All those different devices that we've been discussing are all pretty much right here. So we kind of discuss the evolution of the engine here as we go through this. So looking at this engine, it's a 4-cylinder. You can see there's the 4 injector lines coming off of it, fuel injection lines. Mechanically injected, you'll see there's a oil pressure sender right there in the middle of the picture. Up on the upper right hand side, you'll see a coolant sensor. And that's pretty much all the electronics. You look at the wiring on this thing, and there's not much going on in this harness, that wiring harness on there. So when we get up, this is a 6-cylinder. I believe this is a John Deere engine here. You start looking, there's a few more wires. There's a little bit more wiring harness going on. There's a fuel sensor, there's a pressure sensor, there's a pressure sender. There's a coolant sender, a few other things like that. A fuel rack solenoid, a few things like that. And here we go. Now we get into the bigger stuff. So or into a more modern engine. You'll see in that picture, you can see the ECU, you can see the wiring harness, you can see there's a communications port right there. All kinds of different things. There's probably a sensor in that fuel water separator. There's all kinds of devices that's happening here. So this is a later engine. I believe this is a Tier 4 interim engine. And we got sensors all over the place. I'm pointing them out on this engine here. This is I believe this is a Mercedes engine here. And then here, oops. And now we come into Tier 4 final with DEF. So now we have 2 different fluids we need to put in the engine, and we got to keep all this stuff maintained. So now become a much more complicated engine. These are MTU engine. This is an MTU engine, I believe. With you can see all kinds of different things going on with this engine, much more complicated, a whole lot more electronics happening on here. Again, the same one, compound turbos, all kinds of interesting things happening here. And then we get into a EA Tier 4 final exhaust after treatment. So here we have a graphic. This happens to be a Cummins. This is the after treatment system used on the 1 meg QST30 engine. So you'll see coming from the left, you'll see there's a heater, an exhaust after. So if the exhaust stream is not hot enough, and I believe it's usually around 600 degrees C, if that exhaust stream isn't hot enough, we'll use an actual heater and heat the exhaust stream up to get it hot enough to where um, the catalysts actually work. Then we have a controller there. You can see in the white box a heater controller. On the top side, you'll see the DEF dosing unit, which is a device that determines how much diesel exhaust fluid gets injected into the exhaust stream into the mixer. The first section is diesel particulate filter, which is a device that takes basically the black soot out of exhaust stream, and then SCR, selective catalytic reduction device, which is a catalyst, which is going to react with the exhaust stream and the DEF and turn everything into nitrogen, basically. And here we go schematically how this is all going to work. Starting at the left-hand side, come air into the air filter, goes into the turbocharger, gets compressed, after cooled, and pushed into the diesel engine. Diesel engine then pushes it back into the hot side of the turbocharger, and then that exhaust stream goes into that electric heater we were just discussing. And then DEF, coming from the bottom, is gone through the dosing unit. It's injected into the exhaust mixing tube. And then as we go across as we move right, you'll see the NOx sensor. So that's our first NOx sensor that's looking at the exhaust stream pre-treatment. So it's looking at whatever NOx is in the engine exhaust stream as it goes in. Then it goes into the diesel particulate filter. Now, the diesel particulate filter is just exactly what it says. It's a filter. So what happens to filters? They tend to get plugged up over time. They tend to, as they do their job, they get full of whatever it is they're filtering out. And in this case, it's filtering out soot and ash, and hopefully converting the soot into ash. So how do we sense what's going on? We sense pressure on one side of the diesel particulate filter, and we look at the pressure drop on the other side of it to see how it's performing and what its condition is. So there's two of those pressure sensing devices we were talking about. Then we go into the temperature. We go into the catalyst, the SCR catalyst. So we look at the temperature going into the SCR, and if the catalyst is doing what it's supposed to be doing, that temperature should change. It should actually go up a little bit. And then we can look on the downstream side of that catalyst and see if the temperature has reacted in the direction we think it should. And finally, coming up the tailpipe, you see another NOx sensor, and that NOx sensor is going to say whether we're doing the job or not. So how much have we changed from the input side to the discharge side? So there's all those sensors we've been just talking about, and that's what it looks like in reality. This is Alpha Cummins 15-liter engine, actually. And I sure wish my cursor was working, but I can point out, you see the two big hoses on the right-hand side goes into the DEF dosing unit. If you look at the bottom on where the metal frame meets the thermal wrap, you'll see a couple of devices. Those are the NOx sensors. Then we have a couple of temperature sensors in there as well. All those devices are right there. There's a whole lot of instrumentation needed to keep something like this happening. So this is a diesel particulate filter that got clogged up with soot. You can see where the technician broke that chunk out just so you could see what was in there. But that particulate filter is completely plugged with soot. We don't want that to happen. Effectively, soot is basically the black stuff. We want it to get so hot that it converts that soot to ash. We want to burn that down to a white, very fine powder that's ash. The diesel particulate filter can deal with ash, but they can't deal with that soot. So, all right, let's go back to controls. How much controls do you need? Like, what is the size? What's the complexity? What do you need? What's your project? What are you doing? Is it a standby job? Is it prime? Is it continuous? Are we going to parallel with utility? Are we going to do something small, 10, 15 kW? Are we going to go 2 meg, 4 meg, 10 meg, 100 meg? What is it? What cost? What's our cost? Obviously, there's a cost requirement for everything. What's our budget? What's our performance? How critical is the installation? Is it a hospital? Is it a data center, or is it just keeping the lights on in the house? NFPA 99 or 110 requirements. What's our runtime hours that EPA is going to let us run? Is there any utility? If we're going to parallel with utility, is there any requirements that the utility is going to have on us? Are we going to have some sort of relaying and things such as that? So simple. I like looking at this particular picture because it says farmer owned since whenever it was, and I grew up on a farm. I know how simple farmers like to keep their stuff. So it's got analog gauges on it. Pretty simple looking genset. Then get into something incredibly complicated like this. So there's 6 turbos on here, 20 cylinders, and ECU that probably has more computing power than the Apollo shuttles. And anyway, pretty fancy. So let's talk electronic engines. So electronic engines will have an ECU, electronic control unit, or ECM, which is electronic control module, and sometimes other manufacturers call them other things for level 1 control and protection. Now we'll talk about level 1, level 2, and level 3 here in a moment, but keep in mind level 1 is just on the engine itself. J1939 is the communications is a CAN system, and it's quick, it's fast. J1939 is pretty much the protocol that all modern engines run on. I think since like 1996 or something like that, it became standard. But J1547 is the older. It's an RS-485 type system, Modbus type system, but on some of the older engines before J1939 came in. You'll hear a statement like the only thing standard about J1939 is the name J1939. Yes and no. So there's a whole lot of data that's available in a J1939 protocol, and I'll show you that as we move forward here. But there's just a whole lot of data points that are available, and one manufacturer might use one set, another manufacturer might use another set. So very difficult if you don't have those maps to the protocols. So some manufacturers can accept commands that are written to the comm link. Some of them can't. It's all common now to have J1939 that talks, or you're talking over J1939 to voltage regulators, other devices that are out there, engine controllers, genset controllers, voltage regulators, there's other things that we can talk on that J1939 loop. And then there's other things that the J1939 data can do. It can take other, use that data to say start fans if temperature's rising, or open loopers, or do other things in a system. So how much control do you need? So do you need something as simple as that upper right graphic where it's basically a key and a on-off switch? Do you need single function component, multi-function components? You need dedicated purpose controllers. Are you tying into genset? Are you tying utility to genset to utility? Or do you need to go full on with a PLC, programmable logic controller, including all the programming and all that goes into it? So what are our levels control? Earlier we'd mentioned level 1. Level 1 is on engines. So that's the ECU, the atom, the ADEC, all those different proprietary names. But what's that doing? That's controlling your start, your emissions, your crank, injection timings, or spark timing, all the engine protections, fuel control, all that stuff. And all that is typically provided and locked down by the engine manufacturers. So it used to be these discrete components. Now it's a ECU that does pretty much everything. But this is level 1 is just engine only. Level 2 is a genset now. Now we're going from the engine itself to now we're taking in the rest of it. So the alternator, all those other things, along with the breaker control, sync devices, load bar share, all that kind of stuff, mode selection. And again, it used to be these discrete components, and now it's dedicated purpose controllers. And then level 3. So level 3 happens at, say, if we're going to tie to utility, this is at the tie point. So this will be where we get all the things like utility protections, the relaying, import export power, base load, peak shaving, all that sort of thing. So, and again, this all used to be done by PLCs. Now it's pretty simple to get a controller to do all that for us, all that stuff for us. Excuse me. Here's a typical ECM, and I just like to look in those connectors, and there's a whole lot of pins inside here. Each one of those pins is doing something, and then you got 4 sets of those pins. So there's a whole lot of stuff going on in this controller. And then here's just another ECM. Often they're mounted right to the engine itself. So again, in an ECM system or electronic engine, sensors communicate over the J1939 bus. So that's those temperature sensors, fuel pressure, manifold pressure, coolant, all those things. Crankshaft, camshaft position, RPM. ECM calculates all the timings, all the for fuel, for ignition, for all that stuff, emission controls, and it uses data from all those sensors. The ECM continuously checks and verifies all your input data, protects the engine. It can also derate an engine to ensure compliance. I don't know if you've ever seen, say, driving down the interstate. This happened a lot more, I don't know, 15 years ago. You'd see a semi truck going down the road at about 3 miles an hour. Well, that engine had been derated. Typically, what that means is the ECM derated the engine to get down to where the genset or the truck was only making enough power to keep it rolling down the road to get it off the road and into some safe area, because it had gone out of emission compliance. And it can use alternate control strategies. Say if a coolant sensor goes bad, it can say, well, let's look at the coolant sensor. It's ahead of this in line, and we can look at the coolant sensor that's behind it. Those two are both in control and having good signals, and we can go around that coolant sensor that may be acting inappropriately. And again, with J19 electronics, typically it's like it works or it doesn't. ECM will probably tell you if that sensor has gone bad. So let's talk about fault codes. You'll not see too much of this anymore. In the earlier days, it was more common to have to look at these things. You get your chart out and say DM1. Well, that's a currently active fault. What is that DM1 fault code? Or the DM2, that's a stored fault code. What happened a while ago? What happened, previously? PGM parameter group number, SPN a suspect parameter number, FMI is failure mode indicator, and all these different numbers, all these different codes would give you clues to troubleshooting from back in those days. At current count, how many times has it happened? So here's a little troubleshooting tool that I've used in the past, and so it'd give you your SPN, your suspect parameter number, and it'd give your FMI failure mode indicator, and then you go out and get your manual out and look up those two numbers, and it might tell you some clues to get you troubleshooting in the right direction. Today, most of that happens internally. It'll tell you, sensor whatever is open or something like that. So now, like I said, we're into these third-party controllers that do these kind of things. So, Dive, ComApp, Deep Sea, Woodward, a bunch of different companies are making these type products, and they're specific, and they can even get onto where they say, you can say, I've got a CAT 3516, or I've got a Cummins QST 30, or I've got, MTU 12B 2000 or something like that. And they can give you a a controller, a cable, and everything to make that engine work. You can just get the functionality you desire. You can often program them with a laptop. They're very flexible. They commute over the CAN bus, over the J1939. Very powerful. And then you get into manufacturer specific stuff, which is very similar to the previous, but these are typically, on the left, you see a Cat, the center is a Cummins, the right one is a Kohler. So this is what would come on, on one of those gensets from the factory. Again, typically, you program them with a laptop. You need a communication device, like we discussed at the very beginning of this module. And again, they communicate over that same J1939 CAN bus. And then we also get communication. Again, the J1939 is going to be the bus that all these things communicate over. So here's the genset controller. Then you got the ECM that's on there. The voltage regulator is tied into that. There may be other CIO custom input output modules that tie into that. Maybe something is controlling airflow or controlling a fan or other things like that. So here's the speed round. This is what all is available. This happens to be a series of photos we took when we were doing some development work on a Tier 4 interim engine and genset package, and this happens to be a deep sea controller, 7310 controller. We were looking at the capabilities of what all it would do. Now, these are actually several years old already, so there's more available now on the newer and more modern stuff, but it's still I like to show it indicates what's all available on a modern electronic system. So let's take a look at them. So of course you got engine speed and you got oil pressure. Note oil pressure in three different, is in bar and PSI and KPA. Coolant temperature in both C and F. Battery voltage, charging voltage. Okay, hours, how many hours of runtime and how many times you started it, fuel level and coolant pressure, inlet air temperature and fuel temperature and turbo pressure in three different types of measurement, and fuel pressure, coolant, fuel consumption. How much fuel has this engine used over its lifetime? After treatment, exhaust temperatures, reference torque, percent torque, percent load, nominal frictional torque, crankcase pressure, ECU. It's looking at the temperature of the ECU, atmospheric pressure, air filter differential. How much restriction has the air filter got? Regen. Are the lamps okay? Okay, how much soot and how much ash built up in the exhaust after treatment? What's our operating speed? Is the ECU link okay? Oh, here's the lamps. Oops, wrong direction. Sorry. ECU lamps. More CAN bus information. Yes, that's working. Then we get in. We haven't even started on the output of the power output stuff. So now we're into generator voltage. L1 to neutral, L2 and L3 to neutral. Remember how we talked in NFPA 110, we could switch between the three different things if we needed to see voltage, and we can see them all three simultaneously. We can also see current, all three simultaneously. Earth current, ground current. How much load do we have on the genset? Obviously not much load right now when we were running it, but kW load, percentage, power factor, average, generator load, and kVAR, kVAR percentage, all these different things here. Okay, now we don't need that rotation meter right now because now we know we got ABC rotation. Okay, so all that stuff is available in these controllers. All this stuff is available on the J1939 data loop if it's been designed to give that data out. So this data then goes into a data table. And just so you're aware, there's all kinds of different types of data that comes in, and each one has different sizes and different different values, whatever those type of data bursts are. This is a graphic that just shows what each one of those things that are all the way from a single bit to 64 bit and probably higher by today's standards. So these are all the data tables. Now, when you say J1939 has a lot of information available on it. So these are all, each one of these lines is a different data table. Each one of these lines carries some piece of information. Now, if you'll notice there, the arrow points to page 18 of 55. So from 8, we have another 19, 20, 20, 30, 40, you know, up to page 54. So there is a lot of pages and a lot of data that's available if the ECU is able to write to those, and if your controller is able to see those different data tables, all that kind of stuff. So it's all, it's a place you can go. So manufacturers, when they say, you know, J1939, the only thing common is the name J1939. The difference is that some manufacturers might use some piece of the data table and another manufacturer might use a different piece of that data table. They don't necessarily have to line up. So you couldn't necessarily take a, say, a cat controller and put it on a Cummins, because those two guys might be using different pieces of the data table, even though they're all still talking over that same J1939 protocol. So finally, we get into programmable logic controllers, PLCs, super flexible, typically custom made, typically custom programmed. You have to have somebody who knows how to build it, has to have someone who knows how to program it. And then, you know, will they be around 5 years from now? Will they still be doing this sort of thing? Will they have documented it well enough that the programming, that someone else can come in and make changes if you need to, or something breaks or something like that? So pretty much these dedicated purpose, these third-party controllers have replaced all these PLCs in all but the most complicated of projects. But you still might see these, but they're very specialized. Probably rare you're going to see one today in a new project. You might see these in an existing project that may be a few years old. So what's all available with these advanced purpose power management systems, multiple gensets? So what can we do with them? With all these different controls now, we can do base loading, we can export power, we can peak shave, we can do zero power transfer, which I don't know if the switchgear type guys talked about that, but basically at the tie point, you basically have zero watts between the two, or zero current flow when you make the switch. You can do runtime management, you can do equalization on gensets, you can do fuel optimization, you know, cut gensets out when they get to where they're not running in an efficient place. Load shedding, load add, genset, load generator adds. If you got a lot of consumer control, and then close before excitation, dead bus paralleling, run up excitation for multiple genset starting, and motor starting, high inrush loads, transfer like transformers, things like that have high inrushes. So all that stuff is possible with the advanced power management dedicated purpose controllers these days. So just a photo of a similar system here. So SCADA, which is supervisory control and data acquisition, building management systems like BACnet and things like that, critical power management systems, balance of plant monitoring, overall controls, all that sort of thing can be happened over these type of systems. Ethernet, Modbus, all these different types of communication systems can happen here with these type systems. Of course, internet, remote monitoring, all this stuff. You know, back in the day, this was amazing. You can look at it from anywhere in the world. And today it's like, yeah, I can look at it from anywhere in the world on my phone. And that's this big deal these days. So, in summary, so we discussed the need for instrumentation controls, the discrete and analog signals, or the differences between them. Some of the basic instrumentation, the base pieces that build these systems, some of the system requirements, discussed electronic engines and the different levels of controls. Talked about dedicated purpose controllers versus PLCs, and a little bit of communications and troubleshooting. So thanks for your attention. Any questions? Feel free to raise your hand before we get shut off. But thank you so much. Appreciate you attending these classes and supporting EGSA as well. And good luck in your careers as we move forward.
Thank you very much, Jim.
Thanks, y'all.
We will be joining again tomorrow. Everyone has the link for tomorrow. There shouldn't be any issues. I apologize for the technical difficulty this morning. We tried to get it sorted out as quickly as possible. So we will see all of you tomorrow. Thank you again for your attention. And you should have the links for day 1 through day 3 videos have been sent. So keep an eye out for that. Thank you again, everybody, and have a great day.